Hello, and welcome to the full course session on CFD simulation using SOLIDWORKS, a powerful tool for simulating fluid flow and heat transfer. This is a certified course session, so make sure to fill out the form in the description after completing the session to claim your certificate. You can proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we're dedicated to providing industry-relevant advanced engineering courses. We partner with industry experts to offer top-notch training that equips you with the skills needed to excel in your engineering career. Don't forget to subscribe to our channel for more insightful tutorials and updates on engineering tools and techniques. Hit the subscribe button and stay tuned. Here's a brief overview of what we'll cover in this training video. In the first chapter, we'll introduce you to the fundamentals of computational fluid dynamics and how it is applied using SOLIDWORKS Flow Simulation. This chapter will lay the groundwork for understanding the principles and applications of CFD in various engineering contexts. In the second chapter, you will learn how to model simple geometry in SOLIDWORKS and set up a fluid study. We'll walk you through the necessary boundary conditions and initial conditions to run a simulation, and we'll also show you how to adjust the mesh settings. This chapter focuses on simulating flow through a pipe, a classic CFD problem that offers insights into the various inputs needed for a successful CFD simulation. You will also be introduced to parametric studies and grid dependency tests, as well as learn the concepts of global maxima and global minima. In the third chapter, we will explore the concepts of external simulation and transient analysis. You'll learn how to calculate total flow time and determine the appropriate output time step for transient simulations, focusing on the flow over a cylinder. In the fourth chapter, you will learn how to create NACA Airfoil data in SOLIDWORKS to create an airfoil geometry. We'll guide you through the process of simulating flow over a 2D NACA airfoil and calculating drag and lift forces for various angles of attack. This chapter will deepen your understanding of aerodynamic principles and how they are modeled in CFD. In the fifth chapter, we'll study the effect of valve lifts on mass flow rate in an icy engine valve. You'll learn how to create flow trajectories and perform transient analysis at different valve lifts. We'll also create plots of lift versus mass flow rate, providing you with the tools to analyze and optimize engine performance. In the sixth and final chapter, you will be introduced to the concept of a moving reference frame and the rotating body feature in SOLIDWORKS. You'll apply the MRF approach to simulate flow through a centrifugal pump and plot a pump performance curve. This chapter will help you understand how to model and analyze rotating machinery in CFD. Thank you for joining us. We're excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievement on LinkedIn. Let's get started with CFD simulation using SOLIDWORKS.
Hey guys, welcome to the short course on Computational Fluid Dynamics using SOLIDWORKS. If you are an undergraduate student majoring in mechanical engineering or aerospace engineering, then you might be fascinated about computational fluid dynamics. You might also be a bit afraid about taking a course in computational fluid dynamics because it tends to be mathematically heavy. So that is why we have created this particular course. So this way we will introduce you to the subject in a pace that is extremely comfortable for you. So we will be hiding away most of the difficult details, but we will still be talking about core concepts that you need to know at an undergraduate level. And to make the entire process interesting, you will also be learning a software. So in this case, we will be using SOLIDWORKS to create simple models, and we will also be running CFD simulations. To follow along, all you need is a good internet connection and a copy of SOLIDWORKS with Flow Simulation. So thank you so much for watching this introductory video. Please do subscribe to our channel, and if you have any friends who are interested in CFD, ask them to take this course along with you. Alright, I'll see you guys in the next video. Bye. Hey guys, I hope you're all doing good. In this video, I'm going to be setting up a pipe flow simulation using SOLIDWORKS Flow Simulation. Okay. The reason why I'm choosing this particular problem is it actually helps you learn a lot about computational fluid dynamics. So to get started, what I'm going to do is I'm going to create the geometry in SOLIDWORKS. There are certain things that you need to do in SOLIDWORKS to run CFD. So in this video, I'll be paying attention to that. To get started, I'm going to click on the top plane, and then I'm going to create a new sketch. Alright, so let's create a circle. So in this case, I'm not shooting for a particular geometry, I'm just eyeballing So as long as it looks like a pipe, I'm good. Now, one thing you can do is after you practice this exercise, you can actually look up for accurate pipe flow geometries for which experimental data exists. You can run the CFD simulations and then compare the results with those experiments. That's a very nice exercise. And what I'm going to do here is I'm going to click on extrude, and I'm just going to extrude it till 0.3 meters. Again, this is just an arbitrary length that I'm assuming. Okay, so that looks like a pipe. Then what I'm going to do is I'm just going to add a small thickness to the pipe. So I'm going to create on shell, and then I'm going to select the top face and the bottom face, and let us see, maybe 0.001, so 1 mm, and let's take a look at the preview. That looks okay. So I'm just going to click on that, and that's my pipe. Okay, so what I'm going to do now is I'm going to simulate the flow through this. So let us call this guy as inlet and then the other guy as an outlet. Now, when it comes to computational fluid dynamics, we are interested in simulating the flow inside the pipe. Okay, so what we need to do is we need to create something called as a computational mesh inside the pipe. And in SolidWorks, it uses an automatic mesh generation algorithm for which it requires that the entire solid is closed, also called as watertight. So in this particular case, I'm trying to simulate the flow through this pipe, correct? So the bottom, so the top and the bottom faces needs to be closed, okay? And how do you close that? You do that by creating something called as lids. This is specific to SolidWorks. So what I'm going to do is I'm going to go to Flow Simulation, and you can see that there's this button called Create Lids. So I'm going to click on it, and make sure that you select the face that you want to close. So in this particular case, I'm selecting this guy, and you can see that it immediately draws this blue color shaded area. Now that's going to be the inlet of my pipe. Okay, you need a closed volume in order to create your mesh successfully. And similarly, I'm going to click on this face, and then these are going to be my two lids. Okay, so when you rotate the geometry, you will see that these are closed. Now, if you pay attention and if you know a little bit about CFD already, then this is like a non-manifold edge. If you don't understand what that is, then don't worry about it. But basically, you need these lids to close the geometry. Now, different CFD codes have different practices, but the concept is you need a closed surface so that you can create the mesh either inside or outside the geometry. Okay. Now, once this is done, what I'm going to do is I'm going to set up the flow simulation. The easiest thing to do next is use the wizard utility. So let's just click on that. It's asking me to save the geometry first. So I'm going to save it. Maybe go to documents. Actually, you know what? I'll save it in a different folder. Okay, and I'm going to create a new folder called pipe flow. And let's just call it pipe. Okay, so launch the wizard again. So this helps you set up your CFD problem quite easily. And I'm going to call this pipe flow. With respect to configuration name, don't worry about it. We'll figure those out later. You can add comments in case you're interested. So click on next. Unit system, I prefer SI units. If you're used to some other unit system, go for it. Click on next again. So in this particular case, I'm interested in doing an internal flow, right? We are trying to simulate the flow through the pipe and not the flow on top of the pipe, right? If you have to do that, then that would be an external flow simulation. Again, don't worry, we will be looking at those examples in upcoming videos. So internal, and then consider closed cavities. Don't worry about this option, leave it as default. We'll talk about this. All right, what are the physical features or what are the additional physics that we want to include in the simulation? Now remember that in computational fluid dynamics, whenever you include these physics, additional equations or additional terms or the way the equations are solved gets changed. Okay, and we will be looking at those things in upcoming videos as well. So in this particular case, I'm not interested in heat conduction, so that's not checked. There is no radiation, so that's not checked. There's something called as time dependent, right? So I've not checked that. So what does that mean? So in a pipe flow, the simulation is what is called as a steady flow simulation. That is, after some point in time, your solution is not going to change with time. Now this might sound a bit funny to you if you have never been introduced to CFD, but the whole idea is at the end you get a solution that does not change with time. Okay, and that's what is called as a steady state solution. Now there are different ways to get to the steady state solution. It depends on how the equations are solved. We will be talking about those things a little bit later because those are slightly higher level concepts. So you need to know things like time integration or time marching in order to understand those terms. Okay, so in this particular case we are interested in steady flow simulations, and we are not going to include the effect of gravity. You can do that if you want to, and there's no rotation as well. So rotation is required in case you're trying to simulate something like a centrifugal pump. So moving on, the next thing that I'm going to do is define the fluid that is participating in my simulation. I'm going to be doing a gas flow here. So air is my working fluid. Just click on add so that it's getting added. Now in this particular case, the flow type is laminar and turbulent. What does that mean? Well, you are basically trying to tell SolidWorks what's your flow regime. Now, if the inflow velocity is such that the Reynolds number is greater than 5,000 or 10,000, you can directly use turbulent only. That is going to kick in the turbulence solver. If you're saying laminar, that means that the Reynolds number is really low. If you're saying laminar and turbulent, then the flow solver is going to be using computational models that are valid for both laminar and turbulent flows. Now we'll be talking about what these models are in later videos, but in general that's the idea. Now in this particular case, high Mach number flow, not really. I'm not going to do that. I'm just going to click on next. In addition to this, you can also add something called as surface roughness. So surface roughness is an important parameter that you need to include if your pipe is made up of something like cast iron. Basically the pipe is not smooth and hence it's going to cause additional pressure loss. Okay, now if you include a roughness height, then certain equations are solved which will basically account for this roughness and it would yield an additional pressure loss. Okay, so for now I'm not going to touch that. Just click on next. All the thermodynamic properties and parameters, they look fine. Here you can see that there is velocity parameters. You can initialize the velocity. You can say that at the start of the simulation the velocity is so and so, but in this case I'm not doing that. Similarly, turbulence properties, you can set up some turbulence properties. These things can be really important, but for us we are not going to worry about it. Like I said, these are things that we will slowly learn in the upcoming videos. Click on finish. And immediately you can see this box, right? Basically what SolidWorks is doing is it's calculating something called as a bounding box. It looks at your geometry. It looks at what's the minimum x, maximum x, minimum y, maximum y, minimum z, maximum z, and then it draws a box around your model. And that's what's happening here. Okay, so the next thing I'm going to do is choose boundary conditions, right click, and I'm going to type insert boundary conditions. Okay, so here what we're going to do is we are going to basically say that at this inlet the velocity is like 1 meter per second. So the first thing I need to do is I need to right click and then click on select other, and I'm going to select face at lid 2, and then in bracket you need to see pipe. Okay, make sure that you do not select this. You need to make sure that you select this. Okay, that is basically saying that at that phase the velocity is going to be 1 meter per second. So I'm clicking on that, and here I'm choosing inlet velocity, and let us say 1 meter per second. You're specifying the velocity magnitude here, okay, and you're not specifying the component of velocity. So if you have to do a 3D vector, then that will help you specify your x, y, and z components. So in this case, I'm just going to do 1 meter per second. Now, in addition to this, you can subject a fully developed flow profile at the inlet. So as you know, in a pipe flow, the velocity profile is going to look parabolic, right? I can enforce that profile by checking on this box, but I'm not going to do that. I'm just going to say that the velocity here is 1 meter per second, so that is what is called as a uniform profile. And as the simulation progresses, your boundary layer is going to develop, and we'll see that in the solution. And in the next phase, let's just click OK here and do the same thing again. This time I'm going to right click on the other phase, click on select other, and make sure that you select phase at lid 1, and in the bracket you see pipe. Okay, so that's the name of your simulation, right? That's the name we gave initially. So you need to see that name, okay? Whatever the name that you gave, make sure that you see that. Do not select this option, that's the wrong one. In a later video, I'll comment on why that's the wrong option. So for the outlet, what you need to do is you need to give a different boundary condition, okay? So at the outlet, what I'm going to do is I'm going to select static pressure and I'm going to say 101325. Now, if you're a mechanical engineer, then you might know what static pressure is. If you do not know, try to understand what static pressure is and what's the difference between static and total pressure. Now, with respect to boundary conditions, right? You're solving a partial differential equation, correct? Now, for partial differential equations, you need boundary conditions. Now, the type of boundary conditions that you provide is very important. If you give the wrong boundary condition, then what's going to happen is the simulation is not going to give you the right results. It's going to try its best to get to the solution, but sometimes it doesn't. This is what you say as the solution is not converging. And typically the solution is not converging because the boundary conditions are wrong, or sometimes it has to do with your geometry. So in this case, you can see that I'm choosing a particular combination of boundary conditions. I'm using mass flow at the inlet and a static outlet. Okay, and I say static outlet, at outlet I'm providing a static pressure boundary condition. Okay, so that looks good. Let's click OK here. Now there's another boundary condition that we need to add, and I'm going to just select this guy, the wall, and let me just make this bigger so you can see what I'm selecting. Okay, I'm selecting this guy, and you can see that there's a small arrow there, and I'm going to say that this is a wall. Now there are several options. It says it's a real wall or an ideal wall. Okay, so here we are going to basically say it's a real wall. And you can see that there are additional properties such as wall motion. Again, don't worry about these things. We will learn them in upcoming videos. So let's say OK here. And that's basically it. Now we have almost set up our simulation. The next thing to do is to take a look at the mesh. Now, like I said, SolidWorks uses an automatic mesh generation algorithm. So what you can actually do is just right click on mesh and it says show basic mesh. Now you immediately see the cut plane here, which shows you the mesh size. Okay, so this is basically what you call as discretization, and you can see that the discretization along X, Y, and Z direction is the same. So that is why the element looks like a square. It is possible to stretch out the elements if you want to. So in this case, you can also right click and select, not here, sorry, you can right click on global mesh and click on edit definition, and you can just change this initial level of mesh, and you can see that immediately the mesh becomes finer, right? So if you're using a larger number, you're going to have more mesh points and you can expect an accurate solution. Now we are going to start with a smaller value. So here you can see that SolidWorks provides us a recommendation. It's the initial level of mesh is set to 3. This is going to give us a reasonable solution in a reasonable time. Now in addition to that, you can do something called as an advanced channel refinement. Now when I click on that, nothing happens here, but what that does is near the wall of the pipe, it refines the mesh. Now here what you are seeing is called as an hexahedral mesh. So what does that mean? Now here you can see that along X, Y, and Z, your mesh looks square, right? Which means in 3 dimensions, it's going to look like a cube. Now that is what is called as an hexahedral mesh. Hexahedral meshes can be generated very easily by using something called as a binary tree or an octree data structure approach. Okay, and we'll be talking about these algorithms a bit later. I'm not going to be talking about them in too detail because this is still an introductory class. All right, so now that we have visualized our mesh, let's click on OK. And we're almost set now. So one thing I can do is I can actually run the simulation. And to do that, all I need to do is just press this run button here. And I'm going to run this thing in parallel. Okay, so I'm going to be using all CPUs. Now the default option is use all. Now if you don't have multiple CPUs, that is if you're using a really old computer, then you will see only this option. So let's click on use all and then click run, and that's going to run the simulation. Okay, you'll see a window like this. You can see that the calculation is going on about 49 iterations. You get the answer. Okay, so I'm just going to close this guy, and what I'm going to do now is I'm just going to try and visualize the results. So the first thing I want to do is I want to just hide the computational domain. I don't want to see it. Then I'm going to click on flow simulation, and then I'm going to set up a transparency for the pipe, so that I can see what's going on. The next thing that I want to do is I want to see the mesh inside the pipe, and the way I can do that is by clicking on results, and then what I'm going to do is I'm going to create a cut plane. So let's click on this cut plane here, right click on insert, and you can see that this is the XYZ plane that I'm selecting, and you can see that this green plane is basically cutting the pipe right in the middle, right? That's exactly what I want. And we are going to display some contours. What are we going to look at? Let's look at velocity first. Velocity magnitude, and I'm also going to be looking at the mesh because we want to see how the final mesh looks like, and the mesh is going to be colored in black. And let's click on OK here. There you go. You can see that you have a very funny looking simulation, but that's fine. Okay, the mesh is really coarse, and what's happening is you can see that initially the velocity is all uniform. Let me just put this in straight view. The velocity is initially uniform, but then there is something that is close to what you would call as a boundary layer, and that's going to make the mesh look more parabolic. All right, now again, this simulation is a fairly coarse simulation, and it looks like it did not do the channel refinement that I expected. So let me do something else here. Click on edit definitions. And what I'm going to do is I'm just going to refine the mesh maybe 2 levels more. And I'm just curious why it did not do the advanced channel refinement. That's okay. So let's click on OK now. And let's run the simulation one more time. I'm running this as a new calculation. I'm clicking on run. You can see that it's doing the mesh. I had about 25,000 mesh elements initially, and when I click on this information button, I can see all the details. You can see that we are running at 19th iteration. Things are a bit slow because now there are more cells. All right, perfect. So the solver is finished. So let's close this guy. Okay, so when I click on show again, this time, things look much more interesting. All right, so I'm going to select this guy, edit. Maybe what I'm going to do is just increase the maximum to 2.5. Actually, the maximum velocity is 1.3, so I'm going to set it to that. And let us see. For the color palette, I'm going to just increase the number of levels to maybe 15. Click OK. Yes, that looks much better. And I believe the flow comes like this. Yes. No, actually the flow comes from left to right. Sorry about that. Right, so you can see that the initial velocity profile looks uniform, basically along the x direction. Okay, so if you look here along the x-axis, the velocity is given the same color, right, which means it's uniform. And as I move from left to right, you see the boundary layer appearing, and then you are getting this parabolic profile. So the next thing that we are going to do is we are going to make some line plots and look at this parabolic profile and get some results out of it. Okay, so and I'll be doing this in the next video. I hope you enjoyed this video. If you have any questions, post them in the comment section. I would be happy to answer them for you. All right, I'll see you guys in the next video. Bye. Hey guys, hope you're all doing good. A lot of you had questions regarding how to set up the legend correctly when you're doing a parametric study with flow simulation. So one thing you need to do is, before you run the parametric study, first create the basic cut planes that you want. So for example, I'm just going to create a cut plane. I'm going to be using the XYZ planes, and maybe let me just select the YZ plane. And what I'm going to do is I'm going to be making a plot of the velocity. All right, and then almost immediately you can see that there is a button which says adjust minimum and maximum. So let's click on that, and you need to make sure that you set this to global maximum and minimum. Alright, so now what I'm going to do is, here you can basically reset this to plot maximum and plot minimum, which would also work. Now do not type in numbers here. For example, I've seen that some students type in a value of 10 meter per second or 11 meter per second. That's not going to work, because in your challenge you're changing the Reynolds number, which means your velocity is going to increase. So in other words, you don't want to set the minimum and maximum value of velocity. If you do that, then that range might actually be too narrow for a case with high Reynolds number, and your plot is all going to appear red. Alright, so make sure that this is set to global maximum and minimum. And then what I'm going to do is, I'm going to right click and then select new parametric study. And then we are just going to click on add simulation parameter, and I'm just going to select the boundary condition, and let's just take the inlet velocity and select the velocity normal to the face. You can see that it's initially set at 10 meter per second, and what I'm going to do is I'm going to select this option range with number. So we're going to be starting at 1 meter per second, and we're going to go all the way up to be 20 meter per second, and we're going to have 3 values in between, and click OK. Alright, and then for the output parameter, I'm going to select add results, and I'm just going to select the cut plane, and then I'm going to select the cut plot and click OK. And then if we go to scenarios, we can just click on run. Alright, so looks like we have the results. So now if I click on a plot, you can see that the scale goes from 0 to 1.096 for the first one, and for the last one it goes from 0 to 21. Now this is technically the right plot. Now you can see that near the walls the velocity is lower. This happens because of the boundary layer formation. And now if you create a line probe, then you will be able to get the parabolic velocity profile. Now the other option that you can use is plot maximum and minimum. So let's set that up, click OK, and then we are going to open up our what if analysis, and we are going to go to the scenarios, and I'm just going to make sure that recalculate is enabled, and I'm going to run the cases one more time. So now in this case, if I open the results, you can see that the color variation is still more visible, but don't get fooled. If you look at the values of the legend, it goes from 16 to 21 meter per second. So what's happening is really small values are being cut so that you can actually see the variation. Alright, now for presentations this is fine, but from a technical point of view, both the plots, whether you use global maximum or plot maximum, you're going to get equivalent results, and at the end of the day you will have to use line probes to basically compare the velocities. Alright, hope that makes sense. Now the final note that I wanted to make is, when you go to the cut plot and when you're basically trying to add the legend, never add the values manually, right? So you should never put the max value and min value manually, especially if you're doing a parametric study, and I hope the reason for that is clear. Alright, with that I would like to conclude this help video. Thanks for watching. Bye. Hey guys, I hope you're doing good. In the last video, I had shown you how you can set up a pipe flow simulation in SOLIDWORKS. We set up a simple problem, we got some data out of it, and we really did not investigate it further. So in this video, I'm going to be working towards that. We'll set up a pipe flow simulation, create a line probe, get the velocity and shear stress information, and also run a parametric study. So to get started, let's create a new part file, and the approach that I'm going to be taking towards the geometry is exactly the same. We are going to create a circle first, and then we are going to extrude it. So this time I'm extruding it to 1 meter, so the pipe is fairly long. Once the extrusion is complete, I'm going to select the top face and the bottom face. looks like only one face got selected. So let me select the two faces, and then I'm going to create a shell. Let's click on preview. That looks good. So we've created our pipe, and in addition to this, we'll also be creating our line probes. So now the assumption is, the flow is going to take place, or the flow is going to enter the domain from this side, from the right hand side where my origin point is, and it's going to exit out through this side. So we are going to place a couple of line probes near the exit or the outflow of the domain, and we are going to see how the flow quantities change. To do this, I'm going to put the geometry in the top view and create a new sketch. I'm going to create a line, something like this, and let's add some dimensions. Okay, so roughly at 0.05 meters from the outflow boundary, I'm going to be measuring my velocity profile. And let's exit sketch. And what I'm going to do is I'm going to create one more sketch, and this time the line is going to be behind the first line that we created. Enable smart dimensions, and let us say the distance is 0.1. Okay, so our objective is to plot the velocity, pressure and shear stress across these lines to see how they change. And you can actually learn a lot about the simulation by creating these type of line probes. And in a later video, I'll show you a different problem, which is called as the backward step flow problem, where I'll also show you experimental data that has been measured across these lines. We'll take a look at the relevant paper and the results that were obtained. All right, so now that I have my line probes, I'm all set. So let me save my simulation. I'm going to call this as pipe flow with line probe. So once I've done that, let's click on flow simulation, and we are going to create some lids. Like I said before, lids help us create that closed watertight volume, which is required for CFD simulations. SolidWorks uses lids. In other softwares, it might be called as patches. Okay, so I've created two lids, and I think I'm all set. So let's go to flow simulation, click on new, and the project name, I'm just going to call it pipe flow with line probe. All right, so that's going to be my project. And then let's first get started with the input data. So right click on input data and click on general settings. We are still going to be running a steady state simulation, so this doesn't change. Fluids, so this time we can simulate water flow. We are not interested in cavitation. The flow type is still laminar and turbulent, and initial conditions we are not going to change. All right, so let's click on boundary conditions and insert some boundary conditions. So this is going to be my outlet phase. So let me right click, select other, make sure that you select the right phase. If you didn't see that, let me do that again. Right click, select other. Let me make this guy a bit big. You can see that I have to select this guy, and I should not select this guy. Okay, make sure that you select the one that says face at lid 1, okay, instead of just selecting the lid. All right, so I've selected that, and let's say that this is a pressure outlet, and I'm specifying the static pressure in this particular boundary. All right, so on this side, let's create a new boundary condition. Make sure that you select the right phase and velocity inlet, and I'm going to say that the velocity is 10 meters per second. All right, so I think that sounds reasonable. So the next thing that we want to do is for global mesh, let's take a look at the basic mesh here. That seems like a good starting point, although we just have 4 mesh points across the diameters, which is not good. So what we're going to do is we're going to right click and then So what we are going to do is we are going to right click on global mesh and click on edit definition, and instead of specifying the mesh automatically, I'm going to use the manual option. So you can see that z-axis is basically along the pipe and x and y-axis are describing the cross section, right? So along x and y, we definitely need more points. So I'm going to say 10 points along x and y. Okay, so I think this would be a reasonable first guess. And along z, I don't need 114 points, so let me maybe start with 50 points. So you can see that the mesh is stretched along the z direction. This is perfectly fine. A lot of people do this. And I think we should all be good. So now let's go to results, and then we are going to set up a new XY plot. So this time, we are going to first make a plot along sketch number 3 first. And we are going to be looking at, say, the velocity, okay, velocity magnitude. And then let's just call this plot velocity. And then similarly, we can create new plot for the shear stress. Okay, and then I'm going to select the same line and let me just call it shear stress. Okay, it's also possible to compare the velocity or pressure information between these two lines. So what I can do is, let me create another velocity plot, but this time for selection, I'm selecting both of these lines. With respect to the mesh, I'm going to hide the basic mesh, and we still need to add one more boundary condition, which is the wall boundary. Right click, select other, and let's just make it into a real wall. That's it. So we should all be good now. And let's run the simulation. Okay, I don't have a whole lot of cells, so that's good. So the simulation is complete, so let's take a look at some plots. There you go. So that's my velocity plot. For some reason the shear stress plot doesn't show up. Okay, so I think I have to figure out why that's happening. Let's take a look at the velocity comparison. There you go. So you can see that on both lines the velocity is pretty much the same, which is a nice thing. I'm just going to look for one more plot here. So let me create a new cut plot, and the way I'm going to do this is, I'm going to make a cut plot near the outflow, and I'm just going to see how the velocity looks in that cross section. So the cut plot is already made, so I'm going to make my solid geometry transparent, and this will help me take a look at the cut plot. And I'm just going to edit this guy so that I also see the mesh. So you can see that the profile is not regular, it looks very strange, and this is because the grid that we are using is fairly coarse. So we can perform a parametric study to see how the number of grid points along x, y, and z direction affect our results. So let's hide our plots, and then I'm going to run a new parametric study. So let me first add our simulation parameter. In this case, I'm just going to add the number of cells along x, y, and z, and that's basically all I want to do. Alright, so I have my number of grid points here, and then for output, let's add some results. So we are going to include our cut plot, which is the velocity plot, and all of our XY plots. Alright, so I'm just going to call this analysis grid dependency test. And for scenario, we are going to start with 10, 10 and 50. That's our baseline case. I'm going to copy this design point, paste it, and this time I'm going to increase the number of grid points by a factor of 2. Okay, so let's create one more, and we just repeat the process. So this time it's a factor of 4 when compared to the baseline. Okay, so these are the 3 different design points that I want to run. So when I'm ready, I can just click on this run button. And we just have to wait for the simulations to complete. Alright, so the final design point took a lot of time to finish, but the runs are complete. So let's take a look at the first design point. The results are fairly choppy because the grid is coarse. And as we move on to the second design point, you can see that the choppiness is getting down. And if I move on to the final design point, it looks even better. Alright, so let's take a look at the velocity plot. Alright, so here you can see that the velocity is matching pretty well, and as the grid is getting refined, the velocity is converging to an answer. This is what you call as a grid dependent solution. Now for shear stress, for some reason I'm unable to generate the plots. I don't know why. We have to take a look at it. So the other type of plot that we can do is, you can compare the velocity profile at the different lines in a given design point across the other 2 design points, but this might be a bit confusing. So what you can always do is, for example, all I did is I just clicked on the Excel export button, and it gives us all the velocity plots, and it gives us all the information in a table form. So if you have experimental data for this particular case, you can include that in a table as well and then compare your results. Alright, so I hope this video was useful. What you can also do is run a parametric study where you change the inflow velocity condition or even some of the turbulence parameters to see how the velocity profile is getting affected. Okay, I'll see you guys in the next video. Bye. Hey guys, hope you are all doing good. In this video, I'm going to be showing you how to set up a transient flow simulation using SOLIDWORKS. And the problem that we have chosen is flow over a cylinder. So to get started, create a new part, and in the front plane, we are going to draw a circle. I'm going to set the radius to 0.02 meters. And then what I'm going to do is extrude this circle to create a cylinder. And I'm going to say that the length of the cylinder is 0.05 meters. Alright, so this is the cylinder over which we are going to simulate the flow. We are going to first save this problem. And then now we are going to proceed to SOLIDWORKS Flow Simulation. Here we are going to be making use of the flow wizard. So let's click on that. And I'm going to call this project flow over a cylinder. I'm not going to change the default unit systems. As far as the analysis is concerned, I'm going to be setting up an external flow simulation, and we are going to be doing a time dependent simulation. Alright, so what does time dependent mean? Well, this is what you would call as a transient simulation. So whenever you want to simulate the behavior of a system as a function of time, then it is better to choose a transient analysis rather than a steady state analysis. Okay, so transient analysis is also called as time dependent simulation. So in this case, we are going to be running the simulation for roughly 0.1 seconds, and my output time step is going to be 0.01 seconds. So that means that over the duration of my simulation, I will get 10 outputs. Okay. Then we're going to click on next. We are going to choose air as our default fluid. And then we are going to be using the default flow models. Click next. Next again. And here's an important thing that we need to set up. Now, since this is an external flow simulation, we will be creating a bounding box. And we want the flow to take place along the x-axis. So if you see how I have drawn my cylinder, the flow should take place along the x-axis in order for the flow to go over the cylinder. All right, and the velocity along y and z directions is set to 0. That's it. And you can see that immediately a computational domain is created. Okay, so this is a domain in which the fluid is going to be bound. All right, so the flow is going to go in positive x direction. So the flow is going to enter this huge box. It's going to flow over our cylinder, and then it's going to exit out of the domain. And let's take a look at the base mesh. I think that looks fine. So the first thing that we're going to do is we're going to run a simple simulation and make sure we understand what's going on. All right, so let me click on the run button, and I'm going to start a new calculation, and let us see how it goes. Looks like the simulation is complete, and you can see that it just took a minute to run the simulation. So let's take a look at some results. I'm going to first create a cut plane, and if I rotate the model a little bit, you can see that the cut plane needs to be created in the middle of the cylinder. Okay, so currently you can see that the cut plane is actually made on one side of the cylinder. So what I can do is I can put the model in the front view and move the cut plane to the middle. So now if I rotate the model, you can see that that is where the cut plane is. We are going to be looking at the mesh, and we're also going to be looking at the velocity. Alright, so this is how the velocity distribution looks like. So as far as the velocity distribution is concerned, we need to make a decision if it is right or not. So one thing as engineers you need to think about is whenever you're getting some results from a CFD simulation, you need to apply your judgment, see if it actually makes sense or not. All right, a couple of things that I wanted to do before that is just zoom out a little bit, and then I want to see how the simulation actually takes place. Since this is a time dependent simulation, we are calculating the flow solution accurately at each instant of time. So I'm going to create a new animation, and what I'm going to do is I'm going to use this animation wizard option. The animation time is going to be for 10 seconds, and we are not interested in rotating the model, so let's just click on next. And we are interested in loading a scenario. Okay, we are not interested in just moving the cut plane, we are interested in loading our transient simulation data. So let's click on next, and you can see that we are using the results file starting from 0 seconds to 0.1 seconds. That is the time with which we set up the simulation. So if I click on finish, this is going to occur, and what I'm going to do is I'm just going to move this guy inside my domain and delete this and select my cut plot, right click, and then click on insert control point. Sorry, let me do that again, and we are just going to drag this till the end of our simulation. Maybe you can zoom out a little bit to see everything. And then if you play the simulation, hopefully you see what's going on and how the results are getting developed. So let me just play back the simulation one more time. You can see that the cylinder is initially right there. The flow takes place, and then you will see that the velocity is slowly updated. The velocity field develops, and then after some point it stops changing, and we stop the simulation after that. Okay, so it might also be a good idea to create animations for other flow quantities. But here's an important thing. When you're doing simulations like this, what is the expected behavior? Flow simulation is giving you an answer. Is that answer correct? Well, there are certain things that you can do about it. For example, first I want you guys to set up this problem, and I want you to calculate the Reynolds number for this particular problem. And then what you're going to do is you're going to take the Reynolds number that you calculate, and you're going to increase it by a factor of 10 and 100. And you're going to be setting up 2 to 3 different simulations with higher Reynolds number, and you're going to see what happens to the flow structure. Okay, and then once you have done that, we are going to be increasing the base mesh size, or sorry, rather we are going to be making the mesh finer by editing our base mesh size. Before that, let me just close the animation panel. We are going to be making the grid as fine as possible. Now, if you're running this on a laptop computer, you might not be able to go very far with the grid dependence test, but try refining the grid as much as possible, and then you will be writing a project for this particular problem. All right. So whatever I mentioned regarding the CFD setup is documented in the leaderboard interface. Check it out for the exact problem statement. All right. Thank you. Hey guys, I hope you're all doing good. In this video, we are going to be simulating a flow over a NACA Airfoil. To get started, create a new project, and let's create a new part file. And then we're immediately going to go to Insert, Curves, and we are going to select Curve through XYZ points. So this way, what we're going to do is we have this data file that contains the XYZ profiles or XYZ coordinates of a NACA Airfoil. And with those points, SolidWorks is just going to draw a curve. So I'm going to click on Browse, and here make sure that you select text files, and then you will see the NACA text data. Now this file will be shared with you, so you don't have to worry. You can actually use it so that we are both simulating the same airfoil. Let's click on Open. You can see here that the coordinates are being populated. Just click OK, and if I zoom out, the airfoil has been created. So let's just put the model in the front view. So currently you can see that the angle of attack is 0, right? So which means that the airfoil is not tilted. The first thing that I'm going to do is select the front plane, and then I'm going to create a sketch. And then what I'm going to do is I'm going to select this curve, and using the convert entities, I'm just going to convert that into a sketch. Once I do that, if I zoom in here, you can see that the loop is not closed. So we're going to use the line tool to close this off. Okay, so now we have a closed contour. And finally, what I can do is specify an angle of attack at this point. So let's just click on this guy. And then what you can actually do is you can select Move Entities and click on that drop-down box and use a Rotate Entities option. So here what we're going to do is we are going to be selecting the entities first. So we need to select both our line and the spline. And for rotation point, we are going to select the origin. Okay, so now if I change my angle, you can see that the angle of attack is changing. So typically it needs to be like this, right? So this is what you would call as an angle of attack of 10. All right, so I'm just going to go with this guy and click Apply, exit sketch, and once you have it, you can go to Features and you just extrude the geometry to something like this. All right, so that's how you create your base airfoil. At this point, it's a good idea to save the project. I'm just going to create a new folder called NACA test, and then inside that I'm just going to save this part file. Okay, Now that we have saved it, we can actually go to Flow Simulation, and then we can get started right away. The first thing that I would do is click on the wizard tool, and then here you can just give it a name. The project name can be Angle of Attack Analysis. Click on Next. So here we are basically going to go with default units and nothing to change here. So this is going to be an external flow, and we are going to be running a time dependent simulation. Okay. In total, we are going to be running the simulation for say 5 seconds, and we are interested in getting output every 1 second. Okay. Gravity, you can turn it on if you want to. In this case, I'm not going to do that. Click on Next. The working fluid is going to be air. And if you're trying to simulate really high Mach number flows, you can just check this out. In this case, I'm not going to do that. So let's click Next, and then click Next again. Here we want the X velocity to be 600 meters per second. Okay. So that's the speed of the flow over the airfoil. And then let's just click Finish. Okay. So that's our base setup. I'm just going to put the geometry in this view so that we can see everything. Now, if you select the computational domain, you can see that you will be able to adjust it. Before you do anything, right click and click on Edit Definition. We are going to be doing a 2D simulation. Okay. So what we are going to say is we are going to be simulating only the X and Y directions. Any gradients along Z directions is going to be neglected. So we select XY plane. Okay. When you select XY plane, the direction along which the case becomes 2D is the Z direction. I hope that makes sense. So let's click Apply here. And now what you can do is click on Edit Definition, and you can actually drag the domain size. Now, ideally what you need to do is the region after the airfoil, that is called as the wake region. So you need to make sure that your outflow boundary or your exit boundary is sufficiently placed. So something like this should be good enough. Ideally, people would do something like 5 times the chord length at the inflow and maybe 10 to 15 times the chord length at the outflow. So the distance between the end point of your airfoil and the right hand side boundary should at least be 10 times or 15 times the chord length. Now, depending upon your airfoil and flow conditions, this might change. So that is the typical range that people use. So in our case, let me just extend this a little bit more. Okay. And then that's going to be my computational domain. Now, what is the goal of my simulation? Well, there are a couple of things. So first, what I'm going to do is we're going to be looking at global goals. And for global goals, what we want to do is we want to look at the force, the total force along the y-axis and the z-axis, and maybe also the friction force along the x-axis and y-axis. Sorry, not the z-axis, the x and y-axis. Okay, so let's just click on that. And for global goal, right click, and then we are going to add a surface goal. So the surface that we are going to be selecting is going to be this guy, right? And in this surface, what I want is I want to integrate the entire force. So I'm going to be integrating force along x-axis, force along y-axis, and then let's just click OK. So that's my goal. And what else do I need? Well, I need to define my mesh now. So let's first look at the mesh. So I'm going to click on Show Basic Mesh and put the geometry in, say, the front view so that we can see how the mesh looks like. So this is not a bad mesh. So what I'm going to do is right click, and then I'm going to insert a local mesh. So what does that mean? What I can do is I can actually select this surface on the top, and what I'm going to do is I'm just going to refine the cells over there. So that way what's going to happen is we are going to have cells that are really smaller near the wall, which is very important when you're doing airflow, when you're doing external aerodynamics. Now there are additional considerations that you need to take into account. For example, by looking at the computational mesh, you can see that this mesh is not a body fitted mesh. This is what you call as a cut cell Cartesian mesh. Typically it's not very well suited for external airflow, but it gets the job done. In addition to this refinement, we can do much more, but I think this puts at a very good position to run a basic simulation. Okay, so now that I've done this, I can run the simulation. So I'm going to click on Run, and we're going to do a new calculation, and in my case I have 8 processors. I'm just going to use all of it, and then we're going to run the simulation. So this time as I run the simulation, I'm just going to be looking at some data. So let's just close these 2 windows, and what I'm going to do is I'm going to click on insert preview, and then what I want to do is I want to look at contours, say of pressure. So what's going to happen is as the solution progresses, you can see how the pressure field evolves. Similarly, let's do goal plot, and this time we are going to be looking at the surface force. This is the surface integrated force, say along the y-axis, and click OK. So that's going to be another plot, and what I'm going to do is I'm just going to tile all the windows, and you can just watch this to make sure that your solution is converging. Now, one general thing that I want to point out is when people typically run simulations like this, they look at something called as residuals. So residuals basically says how fine your transport equations or your governing equations have been solved. Now the problem with just looking at residuals is sometimes it's not enough. So the better thing to do is to look at something like the drag force or the lift force and see if it's actually converging to a particular value. So you can see that my lift force is still changing, which means I should not stop the simulation yet. I should keep on letting it proceed. Okay, so we'll check back on the simulation a bit later, and we'll discuss the results. All right, so the simulation has been running for a while, and a couple of things that I'm noticing is that the average value for my lift is converging to a value, which is a good sign. Ideally, I would like to run this for a longer time. So currently you can see that, we have run about 1870 iterations, and it's pretty much flat, which means with subsequent iteration, things are not changing. And this is what you need to do to determine if the solution has converged or not. Now, the other thing that I'm seeing here is there are some reflections here. So for example, the top and bottom boundary, well, we did not define any boundaries, but looks like there are some waves that are reflected from there. This suggests that, this particular length needs to be much more higher. That is, the height of our entrance and our height of the exit needs to be increased. But here the whole idea is we are just demonstrating how to set up an airfoil simulation. This is not a validation study, so we don't have to worry about it. Okay, so at this point, I'm just going to stop the simulation. Okay, so now I can just close this and then head back to SolidWorks. So here we first want to create a cut plot, insert, and then we always like to create XY plane plots. And then we are going to be showing the mesh and also contours. And let's maybe take a look at, say, velocity to start with. All right, so you can see that your velocity contours are there. A couple of features that you should notice is that you can see that near the surface, the mesh is being refined. So that's the refinement feature that we had enabled. And there we go. So that's velocity magnitude. Again, it looks a bit very choppy because the color is not a uniform color. So what I can do is I can just click here, edit, and then what I can do is maybe just increase the number of color segments, and that's going to give you a smoother looking plot. At this point, maybe just click on edit definitions, and then maybe just hide the mesh. And there we go. So that's going to be a much more smoother looking plot, which you can take images and then include in your reports. All right. So more importantly, we need to focus on our goals. So what I can do is I can just click on insert, and let's just look at some of our goals. So for example, we wanted to look at the integrated force. So the integrated force along the x-axis, that's going to be a drag force, and the integrated force along the y-axis is going to be a lift force. So we can just click on show. Then you get the total value. So this is the data that you need, and what you can do is for different angle of attacks, you can calculate the lift force, the drag force, create a plot, and then calculate the lift and drag coefficient. So as part of your assignment, what I'm going to do is I'm going to ask you to change the angle of attack till stalling conditions reach, and then you are going to be making a plot of the drag force and the lift force, and you are going to be writing a project report on that. Okay, so I hope this video provided you enough information on how to set up an airfoil problem using SolidWorks Flow Simulation. If you have any questions, get in touch with us. All right, I'll see you guys in the next video. Bye. Hey guys, hope you're all doing good. In this video I'm going to demonstrate how you can create the geometry for the engine valve analysis. So to get started, click on new and then open up a new part file. And then what we're going to do is we're going to click on the top plane and then we're going to sketch. Alright, so I'm going to start with a circle for my cylinder. And I'm just going to say that the radius is 0.05 meters. Alright, so that looks nice, and then we're just going to go to features, extrude this guy. We're going to extrude it the other direction, and we're going to extrude it for about 10 centimeters. Okay, perfect. So the next thing that I want you to do is click on the front plane again, and what we have to do now is create the intake port. Again, I'm just going to be using approximate dimensions as this is clearly a made up geometry. Now if you're actually working with a realistic model, then you can kind of use the same concepts that I'm teaching in this video, right? So we are selecting front plane, and need to select it again and use the sketch tool. And what I'm going to do is I'm going to use the line tool. Oh, looks like I exited sketch, so let's just click on the front plane again, sketch, use the line tool. I'm going to say that my intake port is going to come like this and it's going to enter like this. And then what I'm going to do is I'm going to apply a fillet, in this case to 0.04. Alright, this is going to be the guideline for our intake port. And let's just click yes, exit sketch. And then what we want to do is we want to just use the sweep tool to construct the intake port. And how I'm going to do that is go to features, reference geometry plane, I'm going to select this guy, and I'm going to select this point. Looks like that didn't make it, so let me just do it again. Click on plane, select this guy first and then this point. There we go. So now that we have our plane, we can just sketch in that plane, and I'm just going to draw a simplified shape. So we are going to say that our diameter is about 0. Maybe, and we are going to say that our radius is 0.02. Alright, so that looks decent, I think. And what I'm going to do is I'm going to use the sweep tool. We have selected the profile, the circle is what we're going to sweep, and this is going to be the path. There we go, that looks nice. Alright, so it looks like the port is a bit bigger, so what I'm going to do is I'm just going to click on my sketch, edit sketch, use the smart dimensions tool. Maybe instead of 0.04 I can say 0.02. Oops, sorry about that. So instead of 0.04 I'm just going to say 0.025 and click OK, click OK again, exit sketch, and hopefully the port should get created automatically. Now the next thing that we need to do is create a valve, right? And the tricky thing about the valve is that it's going to be it needs to be positioned here, right? So we need some reference features for that. But before I do that, I'm just going to create a thickness for this entire model. So let's just use the shell option, click on this face and this face, click on preview, and what I'm going to do is I'm just going to call this 0.02 maybe, and that looks okay. So let's select that, and it's always good to use the cut section view to make sure that the geometry looks correct. So let's click on OK again, and let's disable this guy. The next thing that I want to do is create some reference geometry. So what I'm going to do is I'm just going to create an axis, and I'm just going to use this method. So what I need to do is create an axis. For that I'm going to click on reference geometry, and I'm using axis. Now in order to create an axis, all I need to do is select a cylindrical face, and then SolidWorks is going to draw the axis. So let's just select this cylindrical face, and you can see that we have our axis. All right, Okay, perfect. So now that we have our axis, I think we can select this axis to basically draw a plane. So what I'm going to do is go back to reference geometry, go back to plane, and I'm just going to select this guy. Looks like it's already been selected. So far we have one reference. The other reference that I'm going to give is my right plane, and when I do that, it's fully defined. Let's click OK, and there we go, we have our plane. So now it's very simple. What I'm going to do is just look at it in the normal direction, and you can use the Alt plus arrow keys to rotate the model, by okay. And remember, you can always use the Alt key to rotate the model. So now what I'm going to do is I'm going to draw my valve. Alright, so let's click on the plane and click on sketch. We're going to be using the line tool to quickly draw the sketch, and we're going to start from the axis that we have already created. So let's just go up, maybe a small distance to the right. Again, you can always change dimensions accordingly. So since I'm just going to create a made-up geometry, I'm really not caring about the dimensions. And then create the valve region, the valve lip region, maybe somewhere here. You can also create some reference geometries to make your positioning a bit more tight. Not paying a lot of attention, but you can always do that. Alright, so I think that completes my valve. And what I can do now is I can just uncheck the line tool and select all my lines. I think it looks good. So what I'm going to do now is go back to features. I'm going to use the revolve tool, and for axis of revolution I'm just going to select the axis that we have created, and there we go, and then we selected our valve outline, and if I hit enter, the valve has been created successfully. The only way you can see that is by doing a cut section, and you can see that since we have drawn the valve very tightly, it's actually merged in. What you can actually do is, well, when you are creating the valve, you can just create it in such a way that you push open the valve a little bit, and you can basically use smart dimensions to have the valve open at different intervals. And I think that is something that you should be able to figure out. Once you have created the 3D model, make sure that you are able to move the valves by 1 mm, 2 mm, 3 mm, and so on. Okay, because that's part of your challenge. Alright, so with that, I would like to conclude this video, and I'll see you guys in the next video. Bye. Hey guys, hope you're all doing good. In this video, I wanted to show you how you can vary the lift profile in a consistent manner. So one thing is, when you draw the valve, make sure that you constrain all the dimensions which you do not want to change. So in this case, you can see that the setup looks pretty ugly and intense because of all the dimensions, but you need to do that. So in this case, for example, I am setting the size of the critical valve dimensions and angles. When I do that, what I can do is I can just drag a particular line in the valve, and I can actually vary the valve lift. For those of you who don't know what valve lift is, it is basically the distance by which your valve is actually pushed open. So in other words, if you basically do something like this, this is where your valve is just about closed, so the valve lift would be 0. And if I just open it like this, that's valve lift of 1 mm. Now you can actually set up the lift accurately. What you can do is you can just use smart dimensions. So what I'm going to do is I'm just going to select this point, because that's where the valve is going to close first, and select that horizontal line, and I'm just going to set this parameter to 0.002 mm. Okay, and what I can also do is I can just select that guy. If I want to increase it to 8 mm, I can just type in 0.008, and if I hit OK, there we go. Now you can see that it's pushed open by 8 mm. So this is what you need to do to vary your valve lift consistently. And then what you can do is you can put this as a driving dimension in a parametric study, and with that you will be able to run the simulation. Alright, thank you, bye. Hey guys, hope you're all doing good. In this video, I'm going to be telling you how you can actually change this valve lift automatically using the parametric study option in the flow simulation toolbox. So the first thing you need to make sure that you do is you add the dimension, which basically controls the valve lift. You can take a look at the previous video if you do not know this. Once I've done this, what I'm going to do is, without exiting the smart dimensions, you can actually go to the flow simulation toolbox. And then make sure that you've already run a baseline simulation. Now running a baseline simulation should be something that's very easy. So let me kind of delete my existing parametric study first, and I'll just kind of tell you what I did. I basically just have an inlet. I basically have a total pressure inlet and a static outlet, and that's basically it. And once I did that, I got my simulation. So once I've done that, what I can actually do is I can right click on my flow analysis, and then what I can do is I can click on new parametric study. And when I do that, you will see that you can add the dimension parameter. And what I can do is I can just select my dimension here, which is basically my valve lift. And if I hit accept, you can see that there are several options here. So just click on this discrete values. And what I'm going to do is I'm going to basically select range with number. So here the idea is I can provide a minimum lift, which is 0.001, and I can provide a maximum lift, which can be something like 0.008, and the number of values that I need in between, let us say that I want 7 values. Alright, and let's just click OK here. So that way our geometric study has been set up. The next thing that I want to do is I want to add output variables. Now in this case, the output variables refers to either your goals, or it could be results that you want. So the first thing that I want to do is I want to add some results. So what I'm going to do is I'm just going to have this cut plane here. Let me just delete it and redo it so that you get an idea of how I did that. Let's just delete it and click on cut plane, and then click on insert. So when you do that, it's basically going to ask which plane you're going to use. So we are basically cutting the geometry using the front plane, which is perfectly fine. And I'm going to be, say, looking at the velocity. Oops, not the vorticity, but the velocity right there. And let's just click OK. And this is one of the things that I want. And what else do I need? Well, I'm also going to be looking at the mass flow rate through the outlet. So let me just delete this guy and tell you how I did this. So I'm going to right click on goals, and I'm going to click on surface goals. And what I'm going to do is I'm just going to select mass flow rate, which is right there. And I'm just going to right click, click on select other, and not this option, but just give me a second. Select other. For some reason the lid is not being displayed. So let me just close this guy and make sure that I'm able to select this. Let me go to my flow simulation box, and alright, so let me try that again. So to add, alright, so then what I'm going to do is I'm going to basically, alright, so what I'm going to do is I'm going to right click and add insert surface goals, and what I'm going to do is select mass flow rate and right click, select other, and I need to select the lid option. Click OK. So now I can come back to my output parameters in my parametric study, and for goals I can add the surface goal mass flow rate, And for results, what I'm going to do is I'm just going to select this cut plot, which is velocity magnitude. Let's click OK. As far as the mesh, let's just edit definition. We're just going to run it on a scale of 4. You can look at the basic mesh if you want to, or if you don't want to do it, that's fine. Go to the scenario, make sure that everything is all set up. Now you can see that all of our design points are here, and all we need to do is just click on this run button, and we just have to wait for the simulations to complete. So now that the simulation is running, one thing that you might find interesting is if you apply some amount of transparency and zoom in near the valve, you will see that after the design calculations are complete, the valve will automatically be pushed open a little bit more. So this is really convenient. You don't have to do it manually. You can do it manually if it is just a few cases, but since we are trying out a lot of cases here, it would be great if all of these changes happen automatically. And that's exactly what's going on here, so that saves us a lot of time. Alright, I'm just going to check back on the simulation later to analyze the results. Okay, so looks like the results are complete. So the first thing is, when I look at the cut plane, you can see that, so initially when the valve lift is close to 1 millimeters, the velocities are really low. But then when the valve opens, you can see that there's a really high velocity and the mass flow rate also increases. Oh, alright, and I'm just noticing that I actually forgot to add my goal values. So let me just add the mass flow rate. I thought I added it. So let me go back to scenario and let me see if I can just refresh this, and so looks like the mass flow rate result did not get calculated. So I'll have to run the simulation again. So let me just click on run again, and once I get the results for the mass flow rate, I'll be back. Okay, so looks like the simulation is done, and you can see that for the different design points I'm getting the mass flow rate. I should be able to export this into Microsoft Excel, and I can plot it, and if I have experimental data I can compare, or I can and I can also go back to chart view, and I can quickly look at how the mass flow rate changes. Now remember, in this case mass flow rate is negative, so whenever the mass leaves the domain, it's treated as negative. So that's fine, you don't have to worry too much about it. You can just take the absolute value of this number and you can use that. Now this type of plots are really useful. There are a lot of reduced dimensional solvers like GTPower where they actually use this particular data. Now this data can be obtained either from CFD simulations or from experiments, and having this mass flow rate versus lift data can be used to tune the performance of reduced models like GTPower, so that you can get really accurate results. Okay, so this is all you need to finish your project. I hope the video was self-explanatory. Alright, I hope the video gave you all the information that you were looking for. Good luck with your project. Bye. I hope with this information you will be able to complete your project. Thanks. Bye. Hey guys, welcome to a new video. In this video, I'm going to teach you how to set up a flowbench simulation. So what is a flowbench? So flowbench is a device which is basically used to design intake ports. So the idea is you actually have something that looks very much like an engine, but here the whole idea is you are just testing out the intake port. Now in this case we are having a very simplified port and there is no exhaust, right? That is because in the flowbench you use only the port that you are going to test. So for example, say you are working with a diesel engine and you want a particular swirl. If you don't know what swirl is, it basically says how fast your fluid is spinning about the vertical axis basically. Alright, so let us take a look at the geometry. So if I zoom into the geometry, you can see that the valve is actually open. Now in this case it's open by an arbitrary number. In your case you will be actually doing what you call as a valve lift steady. Alright, so the whole idea is how to simulate how the flow takes place through this chamber, and then what is the pressure loss that occurs. So basically the amount of pressure loss that occurs when the fluid flows through this intake port tells us how well the port has been designed. usually you don't want a lot of pressure loss, because if there is a lot of pressure loss, that is going to increase what you call as your pumping cost. So to minimize that, a port should have as minimum of a pressure drop as possible, right? So how are we going to set this up? It's fairly easy. Now, as far as the geometry is concerned, since this is going to be a mini project, you will be asked to create your own geometry, right? So that's going to be quite interesting. So make sure that you create a geometry like this, and you can try out different port shapes if you want to, right? And for example, if you're interested in trying out a helical port that you find in a diesel engine, that would be really cool. So if someone wants to do that, I would really be interested in seeing how the results look like. And now, as far as the CFD simulation is concerned, I'm just setting up a steady state simulation here. So this is my inlet, right? This is my outlet, and I set up the valve in such a way that the flow is just going to flow around it. Now, since this is a project, I'm not going to give you a detailed walkthrough on how I set it up. You have to figure it out on your own. Now, as far as the mesh is concerned, I'm slightly going with a refined mesh. Now, you might not be able to go up to this level. It depends upon your laptop configuration. So try to go as much as you can. And then you can see that I've also added something called as a local refinement. What is this? Well, in this phase, right, I'm saying that any cell that is attached to my valve, I want to make sure that it is a little bit more refined. And my refinement level is also set to 5. So that's quite a bit of refinement. All right. Now, this is the setting that I have used. Feel free to play with the other parameters as you see fit. Now, I'm loading the results in this case because I've already run the simulation. So in this case, I have results after 0.004 seconds. So let's take a look at, maybe the cut plot. Right. So here you can see that I'm showing the cut plot, and I'll just go back here and hide the engine geometry. There you can see that there's a gas jet that's coming out, and the peak velocity is around 280 meters per second. All right. Now, similarly, you can use the existing outputs to determine a pressure loss. Okay, and that is what you have to do. And you're also going to report the mass flow rate that occurs through this entire flow bench. Okay, that is one thing that you have to figure out. Now, as far as the flow is concerned, let's take a look at how it looks like. All right, so I'm going to click on flow trajectories, and then I'm selecting this phase, maybe start with 20 points. There we go. So you can see that when I do this, I'm able to see the complex flow structure that gets generated. Now you can increase the number of points here to get a little bit more refined image. So for example, if I edit definition, and then here if I say that the number of points is actually 150, this is going to take a little bit more time to process. And then if I actually hide my surface plot that I've made, you can actually see the rich structure that gets developed. Now this is a very simple intake port that has been designed. You can look at the velocities here as well. That's such a cool looking plot, right? Apart from this being cool, you can also get the mass flow rate and also the pressure loss, which is part of your project. So make sure that you do this. In addition to this, you are going to be measuring the mass flow rate at different valve lifts, and you're going to be creating a plot out of it, and you're going to be explaining the plot. Overall, this is a very exciting project. This is something that companies like General Motors or, for example, ARAI, Automotive Research Association of India, they do this whenever, there's a new port. Okay, they do that to see how much swirl is being generated. So doing projects like this is going to look good on your resume. All right. I hope you can get this done. Good luck with your project. I'll see you guys in the next video. Bye. Hey guys, hope you're all doing good. So in this video, we will be learning how to simulate flow through a centrifugal pump. Now for this particular exercise, I will be creating a mock-up geometry, so it might not be that accurate, but it helps me teach you the moving reference frame concept that we will be using to finish this particular simulation. All right, so just make sure that you start with a new part file, and we are going to select the top plane and we'll start sketching. I'm going to select the circle tool first, and I'm going to set the radius to 0.02. Click OK. Now remember, I'm using MKS system, so please make sure that you're So please make sure that you're also using the same thing. And then what I'm going to do is I'm just going to draw another circle here, which is going to go up to 0.04. Now remember, we are typing in the radius. This circle is going to help us guide the blades. Now as far as the dimensions, feel free to change them, but definitely watch the video once to see what I'm doing, and then you can play with the geometry. I'm going to be using the arc tool to create my blades. So that's why I need the outer circle, right? And I'm just going to create one more arc somewhere there, and you can see I'm kind of eyeballing it because, like I said, this is just a made up geometry. Alright, so this is going to be one of my impellers. So what I'm going to do next is I'm just going to use the trim utility, cut this guy, and what I can also do is I can just and then this should be good. So I can exit sketch now. Oh, actually, sorry, we need to go back to the sketch because we need to pattern it, correct? So I'm just going to go to circular pattern selection, and we are going to select one feature at a time. And notice as you're selecting it, SolidWorks is giving you a nice preview. Alright, so we have about 4 impellers now, sorry, 4 blades now. So I'm just going to increase the count to be 5. You can use 6 if you want to, but I'm just going to stick with 5. And then finally, what you need to do is you need to use the trim entities and just make sure that you delete this extra section. Alright, so that way we will be able to extrude this particular shape to generate our impeller. Okay, so I think that looks good. So let's click OK, exit sketch, and go to features, extrude, select this guy. And what we are going to do is we are going to be using the mid plane. Alright, and so 1 centimeter, that should be fine. Okay, so that is basically our impeller. Like I said, it looks really simple, but that's fine. Alright, so the next thing that I want to finish is my volute, or also called as the outer casing. And this time we are just going to go back to top view again, create a new sketch, and we are going to select this guy, and we are going to type in 0.045, right? So our volute is about 4.5 centimeters in diameter. Okay, so that's that. And then let's click on exit sketch, and we are going to extrude that as well. And while you're extruding, just make sure that you select the mid plane option, and remember, we are going to put in something like 0.02, and we are going to put in a distance of 0.015, so that's about 1.5 centimeters. Alright, there we go. Click OK. Alright, now one thing that you need to do is while extruding, you need to be very careful. So for example, here if I go to section view and if I just select my plane, you can see that my impeller is not there at all. Why is that? Well, that's because when I did the extrusion, there is an option called merge result which has been selected by default. You need to uncheck that, and now if I use the cut view, change the plane, you can see that my impeller is present. This is really important. Okay, alright, so this is our volute, and what I'm going to do next is I'm just going to draw a casing on top, and then what I'm going to do is I'm going to draw the inlet runner on the top. So let's create a circle, and we're going to type in 0.015 for radius, so that's about 1.5 centimeters, and this is going to be our inlet runner. Okay, in other words, this is the entry length, and we're just going to say that this is about 7 centimeters long, and type OK. Okay, so the next thing that I want to do is I want to basically draw the exit length, or the next thing that I want to draw is the exit length. So for that, what I'm going to do is I'm going to go to top plane first, look at it from front, and what I want is I want to first create a sketch, and then I'm just going to use a center line. I'm going to be using the circle as a tangent, and we're just going to position our intake somewhere here. So what I'm going to do is I'm going to be using the circle as a tangent, and I'm going to be positioning our outflow boundary or the outlet somewhere here. Again, I'm just eyeballing this. And then what I'm going to do is I'm going to be drawing a line, and I'm going to be using the smart dimensions to measure this distance, and I'm going to say that this is going to be 0.005. Okay, so I think that looks okay. So one more time I just want to enable the cut view, make sure that we are doing okay. All right, the reason why I'm drawing this is I'm going to be drawing a circle here, and I'm just going to be sweeping it, so that way we will get our exit length. So in order for us to sweep, we need to basically define a plane here. So that's fine, we can go to okay, so the next thing that I need to do is draw a circle here, and I need to sweep it along this line. For that I need to create a plane. For that I need to first exit my sketch and then go back to features, and I need to first create a reference geometry, which is a plane. I'm going to select this solid line. Do not select the dotted line, select the solid line, and then select this point right here. Okay, and when you do that, we're just going to basically say set origin on curve and click OK. So now we have a very nice plane here, and we are going to sketch on this plane. Okay, what I'm going to do is I'm going to draw a circle with this as an origin, and I'm just going to use this construction line for my radius. So if you zoom in here, you can see that this is what I'm doing. Okay, and then you can exit the sketch. Alright, so now we are ready for our sweep tool. So let's click on sweep, and we're going to be selecting this for our profile. And if I hit OK, there we go. So my volute is complete. So let's just use the cut view again to make sure that everything looks good. So now you can see that the volute has been merged, but the problem is our impeller is missing. Why is that? Well, if you go back to the sweep tool, there is an option called options. So expand that, and you will see that merge results has been selected. This needs to be unchecked again. And if you hit OK, and let's go back to our section view, modify planes, there we go. You can see that our impeller is there, nice and clean. The problem however is that the volute is not complete, right? So for that, what we are going to do is we are going to use for that we are going to just select our sweep and box extrude 2, which is our volute and outlet runner, and make sure that you select the same two guys. Okay, so what I'm going to do is I'm going to select boss extrude 3. So what I'm going to do is I'm going to go to direct editing and I'm going to go to combine, select this guy, boss extrude 3, and I'm going to select the outlet runner, click on show preview, and we're going to be doing a Boolean operation. We are going to use the add method, and you can see that in the preview all the components are getting joined. So let's click OK. And now if I go back to my cut view or section view, you will see that the connection has been made perfectly and you still have your impeller. The next thing that we need to do is we need to create a shell. So go back to features, click on shell, select this face and this face, click on show preview, and you can see that currently the preview shows that only this can be made into a shell. That's because our parameter, our shell thickness is set to a large number. So let's go to 1 millimeters. And now you can see that the shell is able to penetrate successfully. So if you click OK, what we have managed to create is we have created a perfect volute and an impeller. If I change my section plane, you can see what's going on, right? So we have a solid volute with some thickness, and we also have a solid impeller. Now, an important thing that needs to be done is with this you can run a CFD simulation. But remember, the meshing in SolidWorks is not that great, and hence it's not going to rotate or it's not going to deform the mesh as the impeller is rotating, which it does in real life. So what we basically do is we basically use an approach called as the moving reference frame approach. And what we do is we create a zone around the impeller. Now, what we do is inside this zone, a zone is nothing but a volume. So inside this volume, what we do is we basically add some additional terms in the governing equations which basically simulate the effect of rotation. In other words, we are not actually rotating the impeller, but we are simulating the effect of this rotation by modifying the fundamental governing equations. Okay, so for that we need to create a zone, and let's do that. So I'm going to go back to my top view, but before I do that, what I'm going to do is I'm just going to change the transparency of some parts so that I can see what's going on. Okay, I think that's better. So now let me select top view and look at it in the normal direction. Click on sketch, and I'm going to be selecting this guy. That's going to be the center, and my zone needs to be big enough that it covers the impeller, but it should not be big enough that it actually intersects with the casing. So something like this should do. So always zoom out to make sure that your impeller is completely inside this newly created circle. All right. So that seems okay. So let's click OK here, click exit sketch. And what we are going to do is we are going to extrude. And for extrusion, the same rule applies. Let's just look at it from the side view. You can see that this right here is my impeller. So I need to confine this within that. I'm going to be using the mid plane option. And we are just going to reduce this such that we are just selecting the impeller and nothing else. Okay, so now what I've done is I've created this nice zone around my impeller. So if I rotate the geometry, you will be able to see that. Okay, so this is a very tricky step. You might get this wrong a couple of times. Do check the size of my extrusion, 0.011 meters, and also the radius that I had used for this zone creation so that you can recreate it. Alright, so let's click OK, but before we do that, we need to make sure that merge results has been unchecked. So this is an important step. Alright, so looks like our simulation, looks like our CAD model is set up correctly. So let me click on save, and I'm going to create a new folder called Centrifugal Pump. I'm just going to call this as CP, and I'm going to save it. Note that this is actually, oh, looks like I've already saved a document called CP. So I'll just type in CP_new. Alright, so that looks okay. So now we are ready to do the flow simulation. Okay, so let's go to flow simulation. We are going to be using the wizard. For project, you can just call this a centrifugal pump, CP, click on next. We are going to use the default unit system, so nothing's going to change there. This is an internal flow simulation, and we are going to be doing a steady state simulation. That's why time dependent has been unchecked, and we are going to be using rotation. And here there are two methods. There is local region averaging, and then there is the other method is local region sliding, and then there is global rotation. Now, as far as since this is an introductory level CFD course, I'm not going to go into a lot of details. There is a lot of literature that compares these two methods, so if you're interested in knowing the math behind that, I would suggest you go and read them. Alright, so now that I've done this, let me click on next. And since we are interested in simulating water, I'm going to go under liquids, select water. Just double click, make sure that you've added it. We are not interested in cavitation. If you're interested in simulating cavitation, make sure that you have accurate boundary conditions. If you don't, then things might actually go really bad. So for now, we are not interested in cavitation, so let's just click on next. And we are just going to go with default conditions for the wall thermal conditions and roughness. Click next, finish. Alright, so we get a message saying that the fluid volume recognition step has failed. That is because we have not closed the geometry, so SolidWorks is having a hard time figuring out where the control volume is, where the fluid volume is. So let's click on S because we need to be creating lids. So I'm just going to select this face here to create the inlet lid, and we'll just create this face to select the outlet lid, and we'll just click on OK. We'll just click on S because we need to reset the computational domain. Click on S again. Alright, so now an important thing that you need to do is, we are creating a zone, correct? This zone as it is a solid, correct? So we are basically having the impeller inside this particular zone, the solid that we have created, which doesn't make any sense. Hence we need to take up a special step to let SolidWorks know that, hey, that is just my rotation zone, and that does not interfere with the fluid. It's not a wall, it's not a physical wall. How do I do that? I can click on my input data and click on component control. So here what I can do is I can just select components which I don't want in my simulation. So I'm going to be selecting boss extrude 4, which I believe is our control volume. You can just rotate and see it. So this is our rotation zone. So I've unchecked that, and let me just click OK. Alright, so now let's go to our rotation zone and click on insert rotating region. And then what I'm going to do is I'm going to be selecting boss extrude 4. Right, so when I click on that, nothing happens. You might also experience the same thing. So what you can do is click on select other and just make sure that you select boss extrude 4. Okay, so this has given me problems a couple of times. For some reason, when I select it from the feature tree, it doesn't appear, but when you do it this way, it appears. So we are just going to say that the rotor is going to spin at 1000 radians per second. Again, just made up number. So let's click OK. And I think this looks good. So next we are going to be assigning boundary conditions. So what I'm going to do is at the inlet, I'm going to basically say that I know the value for pressure, and it's going to be just environmental pressure. So let's click on select other, and we have to select the lid. Always remember that. Click OK. So that is my pressure boundary condition. And at the outlet, what I typically want to know is the pressure, because a pump pressurizes the fluid, right? So I typically know the mass flow rate. So I can provide the mass flow rate at the outlet, and I can determine what the pressure is going to be. So let's just click on boundary conditions, insert boundary conditions. And this time I'm going to first clear everything and right click, select other, make sure that we select lid number 1. And this time this is going to be an outlet velocity. And I'm just going to say that the outlet velocity is, say, what, 10 meter per second, or I can go higher if I want to, but that's just a number that I want to stick with for now. So let's click OK. So we have assigned pressure and velocity boundary conditions. So now what I'm going to do is I'm just going to click on mesh, edit definition, and I'm going to be using this advanced channel refinement. Basically what SolidWorks would do is it would basically try to refine areas where the geometry is really small without us making that guess, and it's going to basically do it on its own. Now if you're interested in controlling this, then you can do it. You can go to the manual option and you can kind of play with these numbers, but for now I'm just going to stick with automatic, and let's just click on OK. So with this we have our baseline setup. So now let me just click on run, and what I'm going to do is I'm just going to run a new calculation. But before I do that, I need to do something really important. If I run this calculation as it is, what's going to happen is the simulation is going to converge very quickly. That is because you need to understand that convergence is checked by looking at the equations and seeing if LHS minus RHS is equal to 0. That is what convergence criteria means. This sometimes can be very misleading, and it can lead to a quicker solution. The solutions would still satisfy your equations, but the solution has not yet developed. In other words, it's not always good to use the automatic convergence criteria that SolidWorks or any other software might provide. So what I'm going to do is I'm just going to right click on input data and click on calculation control options. So now I'm going to uncheck everything except for iterations, and I'm going to say that I need to run for at least 500 iterations before the simulation stops, right? So this is going to be my criteria for stopping, and it says at least one needs to be satisfied, and since I've checked only the iterations, that's going to be what SolidWorks is going to be looking for. And then for goals, what I can do is I can just insert a surface goal, and I'm going to be selecting the outlet face, which is nothing but lid 1, and what I'm going to be looking at is the average value for total pressure in that face. Let's just click OK, and we are just going to run this. I'm going to be using 16 cores. It's going to be a new calculation. Let's just run it. Alright, so you can see that I'm also getting this nice preview. That's because I've set it up. So what you can do is you can just go to insert, you can click on preview, and what you can do is you can select a plane, and you can basically go to settings and pick the variable that you want to look at. Alright, so we are just going to wait till all the 500 iterations are complete, and then we are going to check back on the results. Alright, I'll see you guys in the next video. Bye. Alright guys, welcome to a new video. In the last video we had set up the geometry and we had run the simulation, and in this video I'm just going to be looking at the results. As you can see, 500 iterations are complete and here we are looking at the total pressure at the outlet, and look at how nice and steady that is. Initially during the start of the simulation it's just changing, but after some time you're seeing that it's actually flat. This is the type of convergence check that you need to be doing with the variable that's important for you. Now it doesn't matter which simulation it is. You might be doing a different type of CFD simulation. Don't just look at the solver's convergence criteria. That might actually be skewed, and sometimes it can give you incorrect results, and you might be wondering what went wrong. So always look at physical quantities and see if they're actually converging or if they are exhibiting some type of periodic behavior. That's what you need to look for. Alright, so one thing that I wanted to mention is that I made a change which I forgot to record. So under calculation control options, you would have noticed that the goal convergence would also get checked in automatically. Now in the previous video you might have not seen this because we actually set up the goals afterwards. So what the solver does is it automatically checks in that, and this is bad because if this option is checked in, the solver actually stops before 500 iterations. So for me it actually stopped at 173 iterations. So I stopped my simulation, went back, unchecked this and reran the simulation till 500 iterations. So if you are noticing that your simulation stopped at 180 or 190 iterations, that's because this goal convergence criteria has been checked. Uncheck it and you should all be good. So now let's look at some results. The first thing that I'm going to be looking at is some flow trajectories, because that helps me understand how the fluid is moving around. For this, I'm going to be selecting my intake face and also my outlet face, and let's start with say 200 points. And if we just click OK, this is going to take some time to calculate. Alright, so perfect. So I'm just going to hide the geometry for now to understand how the flow takes place, and we're also going to hide the computational domain, alright, so that we can see what's happening. So you can see that the flow is taking place in the right direction. So I can right click and play to understand how the flow takes place. So you can see that the flow is spinning and then it's getting sucked in at the low pressure region that's created by the impeller. That's what causes the high velocity, and then it's spun, and then it actually goes out through the outlet at a higher pressure. When I look at this, I do see that there is some amount of recirculation being created. In other words, the fluid is spinning unnecessarily. This typically means that the pump has been designed badly, which in this case is true, because we are using a made up geometry. Alright, because clearances are really important. You need to have good clearance. You need to have the right amount of clearance between the impeller and the casing, because that determines how much vacuum the pump can generate so that it can suck in the inlet fluid. Alright, so but qualitatively this result is not bad. Okay, so you can also play with other type of plots to understand how the flow takes place, but I think this single animation does the job of explaining how the moving reference frame approach can be used to simulate pumps using SOLIDWORKS. Alright, so based upon this, your task is to actually perform a parametric study for your final project. So for your project, so based upon this, your task is to perform a parametric study. So what you need to do is, first let me just stop this guy, right click, and you can click on a new parametric study, and the parameter that I'm going to be adding is just the boundary conditions. So what I'm going to do is I'm going to take the outlet velocity, add that, and just maybe provide a starting value. So we are starting at 10, which I think is okay, and maybe we can go up to say 30 meters per second, something like that, and we can maybe use 5 values. Now what we are trying to do here is create a performance curve. So we are basically increasing the flow rate, and we are going to compare how the outlet total pressure is going to change. Ideally, if you have a realistic geometry, then you can actually refer to the pump's performance curve and provide realistic boundary conditions. But since we are using made up geometry, I'm just going to make up these examples. So there is a good chance that some of these examples might fail. Your task is to actually run it, and your task is to actually run it and explain the results that you're getting. So as far as the setup goes, make sure that you do something like this, and if I click on open, I need to select my output parameters. I definitely need the total pressure at the outlet, because that's going to be the goal that I'm measuring. Now you can add additional cut planes, you can add additional cut plots or surface plots to get more interesting results. And once you get the different scenarios, interesting. So looks like there's just one scenario. So let me just click on this guy. Oh, that's because my n is set to 1. I'm just going to change this to 6. I'm just going to change that to 6 and click OK. Oh, and this one, let's go back. Let's change this to 20 meters per second. Click OK. Alright, there we go. So now if I go to scenario, hopefully I should be able to see everything. Now all of these cases are going to be running till 500 iterations. So that's the best part. So what I can do is I can just hit submit, and since this is a project, I won't be discussing the results that I get, but when you run this, you will be getting the velocities at the outflow as a function of you'll be getting the total pressure at the outlet as a function of the velocity. So you can use both these data sets to create a pressure versus flow rate plot, and that is going to be the result that I'm expecting from your project. Alright, with that I would like to conclude this video. Thank you. Bye.